series. The Institute of Eminence scheme was launched by the Government of India to empower higher educational institutions and help them to become world-class teaching and research institutes. IIT Madras is proud to have been selected as one of the such Institute of Eminence. A total of 68 research initiatives belonging to 25 identified clusters are presently underway at IIT Madras. As part of these initiatives, the IRIS webinar series aims to showcase the innovative research being generated to various stakeholders like students, researchers, industrialists, and policymakers. From the microelectronics and integrated circuits technology cluster, the research initiative being presented today is titled Photonic Integrated Circuit, which is led by Professor Vijay Krishnadas. Professor Vijay Krishnadas obtained his master's degree in solid-state physics from Vidyasagar University, India in 1996 and PhD degree in integrated optics from University of Paderborn, Germany. Since August 2006, Dr. Das has been associated with the Department of Electrical Engineering, where he is presently holding a full professor position. At IIT Madras, Professor Dr. Das has been dedicated to the development of in-house silicon photonics device technology. Starting from the scratch, he has graduated 6 PhD research scholars and as many as 15 MS research scholars today, all contributing towards the establishment of Center of Excellence CPP-ICS starting from 1st January 2021. We have also Professor Enakshi Bhattacharya, one of the co-PA, is a senior faculty member in the Department of Electrical Engineering, has also joined us today. She has been visiting scientists as Micromine Products Division, Analog Devices, Cambridge, USA from 1990 to 2000. The Center of MEMS and Nanophotonics, funded by MITI, was established in 2011 and recently funded again as part of the consortium Nanoelectronics Network for research and application under her leadership. Today, Professor Shayan Mukherjee has joined as a moderator and he is a professor at the University of California, USA. His research interests include on-chip silicon and lithium niobate photonics for quantum and microwave applications. He is our Vajra faculty since 2019 for a period of 3 years. He has already paid his first visit in December 2019 for 1 month, and our research scholars are already in touch with this research group in exchanging ideas and knowledge. Prior to his Vajra assignment, he offered a Gaian course in silicon photonics, linear, nonlinear, and quantum integrated optical devices and circuits together with the principal linguist of his professor. It's really our pleasure and honor to welcome you all to the 55th webinar. Before we start, a note to the participants: kindly use the Q&A box to enter your questions and kindly upload the questions that interest you so that the moderator can take it. Over to you, Professor Vijay. Thank you.
Yeah, Lisa, you have not introduced our another speaker, Professor Biomedical. Yeah, so is it visible on my slides?
Yes.
Okay. Just 1 minute. Hi, good evening to you all, and also good afternoon to my European colleague and friends, and of course, good morning to our US friends and colleagues. So today, this webinar all about photonic integrated circuit, and this is one of the area chosen by our Institute of Eminence committee for establishing a prospective center for excellence, center of excellence. And you know, this photonic integrated circuits, actually it is a vast area today. Different type of technology platform used for photonic to implement photonic integrated circuits for various applications. But what it means to us at IIT Madras is silicon electronics plus silicon photonics can be co-integrated, electronics and photonics. That is what photonic integrated circuit. Of course, this is the platform actually dominating at this moment for the industry. And of course, I have picked 2 latest news for you to introduce photonic integrated circuit and how it is progressing and how it is meaningful to the industry. It is just March 5, 2021, Intel Corporation announced that it successfully integrated its 1.6 terabit per second silicon photonics engine with its 12.8 terabits programmable Ethernet switch. Okay, and then very recently, August 18, just last month, Xanadu and I make partner to develop photonic chips for quantum computing. So they are developing actually wafer scale photonic integrated circuit, all the technology process development they are developing. All right. So if you just consider only silicon based photonic integrated circuit, of course it is CMOS compatible technology. And CMOS compatible technology means actually you can use all the CMOS process line. I've just borrowed one this image from AMF Singapore and Advanced Micro Foundry Singapore, and where you can see using CMOS technology one can demonstrate waveguide, of course, and then you can use your waveguide devices and modulator, photodetectors, and of course many more passive and active devices along with co-integrated electronics. And if you just consider what is extra for silicon photonics using CMOS compatible technology, that is nothing but waveguide core and cladding. They are actually made out of silicon. Majority of the devices we demonstrate using silicon core, and cladding normally we use as a silica. So that is actually native oxide you get in silicon. And apart from that, additional, very lately, silicon nitride also introduced as a core material because of the transparency you see in the x-axis. If you see here, the wavelength range. So in silicon, you can see it is starting around 1.12 micrometer to, it can go up to almost 8 micrometer transparency. Whereas silicon nitride, if you use as a core material, it can push just towards the visible region also. And of course, you have to see which material you are using as a cladding. That transparency also matters to operate the which wavelength you are choosing. So nevertheless, what we see that majority of the operating window, whatever this is starting from, say 1 micron to up to 3.4 micron, you can actually demonstrate most of the devices which can be useful for various applications. So not only for this, whatever the silicon photonics engine or quantum photonics application, you can find many more applications. Here I have listed few. So they starting from on-chip optical interconnect to lab-on-chip biomedical application, neural network, artificial intelligence. Of course, I mentioned quantum computation and key distribution, and microwave photonics also has a lot of applications you can find in using silicon photonics technology for particularly civil radar system and avionics, and also 5G and future networks that is also coming up very lately. So now what we do at silicon photonics, what we have developed silicon photonics technology at IIT Madras, we have starting from the scratch, as it is mentioned, that we have already have our own technology to demonstrate silicon waveguide passive devices along with integrated microheater. This is the process line we follow, and whatever design we use to fabricate all these devices, that is actually compatible to CMOS process lines. So using that thing, actually, we have demonstrated a lot of complicated devices and with critical dimensions. That is actually whatever this image, if you see, this is some kind of nanometer scale dimensions that could be fabricated in our lab here in IIT Madras using CNNP facilities. So whatever the facilities available here, next speaker, Professor Inakshi Bhattacharya, she will be actually giving you an overview what are the facility available for silicon photonics and other things. And here, if you see, we could actually demonstrate not only the devices like waveguide, just some fundamental building block for the integrated photonic circuits like Mach-Zehnder interferometers, micro-ring resonators with very high Q value, more than 10 to the power 5, and also some of the devices we could fabricate by integrating phase shifters. Here you can see 5 different integrated phase shifters are there, by which we could actually program this 2x2 Mach Zehnder interferometer, which is actually a basic building block for any programmable photonic integrated circuits. And also we could demonstrate micro ring resonators that could be useful for quantum photonic sources that can be programmed with some kind of phase shifter integrated, which can be operated at very high power level also, just beating the bistability of the devices. And a DVR structure that would be useful for various type of filter applications that we could demonstrate. And apart from that, we also have taken up some technology, as I mentioned earlier, that because of the transparency and the loss of the waveguide technology, etc., we've started also silicon nitride waveguide core technology starting from the scratch again. But this time we are doing as a wafer scale, so that at least in the wafer scale we can deposit silicon nitride using our in-house LPCVD systems, and also we have our very good quality e-beam lithography system, so we can pattern them. We can also integrate micro heaters. Also, we have some facilities to integrate also some kind of active devices like diffusion doping, so that you can go for modulator, etc. So, but in this case, of course, in silicon nitride, we cannot integrate for this type of active devices. But what I mentioned in the previous slide for silicon photonics, silicon on insulator substrate, we could do a lot of active devices for controlling purpose, high-speed controlling. But for certain applications like quantum photonic applications, where you need very low loss waveguide structure and also microwave photonics, various level of filter application, etc., silicon nitride waveguides are very useful. So we have taken up this project. And to achieve all this, I want to give you some flavor how we actually progressed to get up to this point. If you see, in 2007, we have started our silicon photonics research from the scratch. At that time, we had only 5 micrometer technology. We could actually demonstrate 5 micrometer devices, waveguides. And then it took about 5 years when actually we could establish our Center for NEMS and Nanophotonics, where we could actually install a lot of advanced technology, advanced process equipment for nanofabrication of the nanoscale fabrication, I would say. And then it took again 5 years to demonstrate a good quality, that means world-class, that means industry standard devices like a high-Q micro-ring resonator, as I mentioned, that is exciting around 10 to the power 5 or so. And once we could demonstrate this high-Q micro-ring resonators, then we were a little bit interested on quantum photonic applications, and then particularly for entangled photon source, which is actually the fundamental building block for qubit generation. And then following that, you can integrate many more integrated photonic circuits for linear optic application, unitary operations. That is actually, we got the first grant in 2019 for quantum photonics devices. And then now onwards, actually, we thought of that not only just a source, we could actually use them efficiently in a on-chip, so that we can actually use for different type of advanced application like quantum QKD, quantum computation, etc. For that, we have also demonstrated on-chip high extinction filter that is exceeding 60 dB or so. That is actually somehow it's kind of world record on-chip filter demonstration. I think particularly using DBR when you talk about DBR. And very recently, we have, because of our this advancement and also progress, we got a substantial funding for establishing a center of excellence namely Center for Programmable Photonic Integrated Circuits and Systems. So that is how we could progress till today. And I will just give you very quickly what we have taken up in this program, in this center. That is, at a glance, this program in summary we have given here. So it is actually for manpower training, because this is the growing industry, a lot of skilled manpower needed. And as a deliverable, we have taken up 3 different products that should be in 3 different sectors, namely that microwave photonics and quantum photonics, and also quantum key distribution for secure communication, etc. And we do have also startup plan. We have already generated 3 patents also, just want to exploit them. And we have industry partner also, System in Package, the SI2 Microsystem in Bangalore. They are very well known for packaging electronics chip. Now they are also into the photonics chip packaging and involved in this project. So that would be, I think, the facility we are generating, that would be first of its kind in India. And also we have to just somehow in India we don't have so far many countries, you know, Europe and America, they have a roadmap for silicon photonics technology, but we do not have in India. So we have also taken up some initiative to have some kind of techno-commercial road mapping for national and international contribution. And also for that, we have a very experienced core team of investigators. As Ms. Leija introduced, Professor Enakse Bhattacharya is there, and Professor Janaki Raman, who is actually expert in electronic chip design, tape outs, and also digital signal processing, who is also helping for developing control devices for our photonics chip. And Deepa Venkatesh, Professor Deepa Venkatesh, Professor Anil Pravakar, they works in the system level. Both are working long time for microwave photonics as well as quantum photonics area. And then in the process line, I think Professor Nandita Dasgupta and Professor Amita Dasgupta also contributing for this thing. And one of our senior faculty members, Professor Kishtopar, who is actually helping us to interface industry and our commercialization, techno-commercial road mapping. He is a very good contributor for this center. And apart from that, as I mentioned, that SI2 Microsystems is actually collaborating us efficiently, effectively, and they are actually executive director, Mr. Soni. We do have weekly meetings, and we are developing the packaging rule for our photonics chip, fiber pigtailing, and also hermetic sealing, etc. All those type of things we are developing. And Mr. Solomon, who is one of our alumnus, actually he came back after 10 years of his industry experience and joined as a chief technology officer for this center. And of course, our international collaborators, Professor Bim Bogarts, he will be presenting some of the global scenario in the area of integrated silicon photonics. And we are all looking forward for his talk also. I think that he is actually one of the pioneers in silicon photonics technology. So I think for silicon photonics industrialization, his contribution actually is phenomenal. And then another collaborator, Professor Jose Kapmani, he is one of the champions in the programmable photonic integrated circuits. He is also closely interacting with us. And we will have a lot of in future. We will have a lot of exchange of students and faculty can happen between University of Kent with Professor Bim Bogart's group as well as Professor Jose Kapmani's group in University of Valencia. And then Professor Sayan Mukherjee, I think he is a well-known face in our department. He has given lectures for our students here, and also associated in our department since 2019 as a Vajra faculty. And he is also giving us a lot of inputs for the center development and establishment, weekly meetings, etc. We are regularly doing between students from his group and our group, and that contributing a lot. And then our assets are a lot of research scholars, very senior research scholar like Arnab, and the latest youngest one, Jasraj, who all are contributing for this center, along with a lot of project staff, and technicians are available and they are joining. And along with that, we also are looking for constantly looking for good motivated PhD students, MS research scholars, as well as postdocs. And if you are interested to learn a little more about our centers, the progress, day-to-day progress, we are updating in our website. So you can visit our website, and any information, etc., you can directly contact us. This is our address given. And with this, I just I think this is my time slot given. I think I have taken that time slot a little more. I think after that, I request Professor Enakse Bhattacharya to present whatever the facility available at Center for NEMS and Nanophotonics. And over to you, Professor Enakse.
You have to stop sharing.
Yes, just Uh, yeah, I did.
Hello, everyone. So let me quickly take you through the genesis of the Center for NEMS, Nano Electromechanical Systems, and Nano Photonics. As Bijoy just mentioned, it was established in 2011 with funding from Ministry of Electronics and Information Technology, Government of India. And that was a 5-year project. Since 2018, we are now part of a national nanoelectronics network for research and applications, NNETRA, with IISc and 4 other IITs. And now it is sponsored jointly by MIT and Department of Science and Technology, and also IIT. So the general objectives are to pursue cutting edge research in these areas, manpower development, developing social relevant systems in health, food safety, and communication sectors. Because it's mighty, they also want these devices to be taken into products, made into products, and also undertake projects from government agencies like defense, space, etc. So this was the first time there was so much investment in nano electronics and nanotechnology by the government of India. It actually started 5 years earlier than 2011 with Indian Institute of Science and IIT Bombay. Because it was a success, it was extended to 3 other IITs. And as you see, we have been on it for now 10 years. So the highlights of CNNP, we had about 50 crores budget, and we already had an existing microelectronics and MEMS lab, again built through sponsored projects, government sponsored projects. There were contributions from two national programs on smart materials. So, but for MIT, we of course had a large input of sophisticated equipment, which really enriched. And as Bijoy showed in his roadmap, suddenly from 5 micrometer technology, we could go down to much smaller structures using e-beam lithography, etc. So we have about 5,000 square feet of class 1,000 clean rooms, and out of which 300 square feet is class 100 for lithography. We have 28 faculty members across 5 departments. As core faculty, there are many more users. We have 5 permanent technical staff, all from electrical engineering. And of course, these numbers keep varying: project staff, postdocs, students. Yeah. So we have 82 users from IITM besides the core faculty, and we also cater to external users on payment, and we have about 40 to 50 users. We have a regular training program, short-term courses, continuing education program, besides, of course, students who go through our institute as MTech, MS, PhD students. So CNNP, at the end of it, we had 13 patents, 176 journal papers, 1 technology transfer, and 1 startup incubated. We really need to improve on this number. The specific areas we worked on for CNNP were RF MEMS, gigahertz resonator, MEMS, NEMS, nanophotonics, and actually Bijoy is the pioneer of silicon photonics in India, and he's really taken it to great heights, and that is the reason that a new center is born now from CNNP. We also do some optical MEMS, lamellar grating for Fourier transform spectroscopy. Then from mechanical engineering, we have diagnostics in nanometer scale using ultra nanoscopy. Also from mechanical engineering, a lot of microfluidics work. So these were what were deliverables in CNNP. Besides that, of course, the equipment is used for other areas. There are researchers in graphene, diffractive optical elements, gallium nitride, flexible electronics, plasmonics, and new faculty members have joined. The next webinar is on these last 2 topics, memory devices and neuromorphic devices. So what are we capable of? Lots of processing, micro machining, deep reactive ion etching, wafer bonding, the standard oxidation, diffusion, rapid thermal processes. We have UV lithography, deep UV lithography, as well as E-beam, several CVD, chemical vapor deposition processes, and RIE characterization, etc. Looks like my 5 minutes are already up. So rest of them are really pictures. So this is, why is this not going off? Okay. So we have, again, this is just a pie chart of the numbers that I've already shown you and the different areas that are given. We actually made a reasonable contribution to both nationally and internationally. As you can see, many of our students are faculty in India. They've gone as postdocs, they've joined industry among PhD students, industries abroad, industries in India, research scientists that is in government labs, and a few startup. Again, this number has to improve. As far as our MS scholars are concerned, the maximum of them go to industry in India. So that is the highest contribution. And of course, some of them continue for PhD, both in India as well as abroad. So rest is, just a lot of pictures. These are equipment that are already available for the Photonics Center, and mainly various CVD processes. We also do some amount of packaging like wire bonding, dicing, etc. And the upcoming facility for silicon photonics is as part of these centers, both the IOE as well as the MIT sponsored centers. We're going to get some chemical, mechanical polishing, etc. So we just hope that with all this, the program will reach great heights. And here are some of the structures that have already been made. Thank you very much.
So now we have Professor Bim Bogers. He will be presenting a little longer, and because he has been involved in silicon photonics for a long time, so I suggested him to give a clear picture about what is going on around the world in this particular hot area of research. And,
why am I not able to unshare?
Professor Bim Bogers, what do you please?
All right.
Hi.
Thank you for the introduction. I'm very, very happy that I can be part of this collaboration, this center. And you asked me to give an overview about where to go or what an outlook on research or global research in photonic integrated circuits, which is kind of a challenging thing to do in 15 minutes. So I'll try my best here. I'll try to give a perspective. I'm not going to go into details, but I hope at the end, there's going to be much more open roads than there were at the beginning. So as you probably all know, manipulating beams of light is a very useful thing to do. We like to play with photons. We like to play with light because light contains a lot of information. Unfortunately, if you want to do it at a bit of a complex scale, it becomes difficult, expensive, and not really scalable. Once you grow beyond the size of an optical table, it becomes a problem. And so the solution to do this is I'm not showing my slides. I'm very sorry. Here we are. Sorry. So, so if you end up with optical tables full of equipment, at that point, you cannot go further in that direction. So the solution is to go to a chip. Essentially, just like in electronics, bringing more and more complexity together on a single chip. And that's the whole story of silicon photonics and all the other photonic integrated circuits boils down to making sure that you can do more complex functionality than you can do on an optical table. Now, the functions that you want to integrate on a chip are waveguides. You need to transport light. You need to filter light, so wavelength filters, but also light sources, modulators, detectors, all kinds of complex functions. It's not the same as transistors, but in the end, you use these devices to do optical manipulations that you cannot do anymore on an optical table. Now, if you look at these photonic integrated circuits, the materials that are being used in general for photonic integrated circuits are quite diverse, because the best materials for light sources are very different than the best materials for waveguides or for detectors or for modulators. And so the result is that we've seen over the past 20, 30 years is a proliferation of new material systems for photonic integrated circuits. And all of these material systems are still living side by side. It's not like in electronics where 99% of electronics is CMOS. In photonics, you still see that there's a wide variety of 3-5 semiconductors, lithium niobate, and one particular one little block that is also becoming quite large and is supposed to grow much faster actually than most of the others is silicon. And so silicon photonics plays a very important role if we look at the future of photonic integrated circuits. And it's very important that this center focuses on that technology. And why is silicon so important? Well, it was already mentioned by Bijoy earlier. Essentially, it's the technology that allows you to make photonics in the same infrastructure as electronics. So you can use a CMOS fab, which is really good, and build really complex photonic circuits in there. And that gives you two essential scale advantages. On one part, you have that large scale manufacturing. You can build your circuits in a technology that can be mass produced at eventually very low costs. As long as you make enough chips, it's gonna be cheap. On the other hand, the scale advantage that silicon photonics gives you is sub-micron scale waveguides. You can shrink your waveguides down to very, very small features, sub-micron waveguides. And as a result, if you compare silicon photonics to different technologies for integrated circuits, you see that if you go from low contrast silica down to silicon photonics, you get a 10,000 or even 100,000 times increase in or decrease in footprint, and therefore an increase in density, which means you can put many more components on the same chip, which means you can make your circuits more complex, which means you can do things that you couldn't do before. Because like in electronics, the functionality of a circuit does not necessarily come from the individual blocks. It comes from stringing all these blocks together and cascading them to do something useful. And so over the past 20 years, we've seen an exponential growth of circuit complexity in silicon photonics. And nowadays we're at a state where you have between 10,000 and 100,000 components on a chip. So you can basically say that this is Moore's law. Now there's a catch, because silicon photonics is compatible with CMOS fabs. That means to really get the best out of your circuit, you might need a CMOS fab. So who fabricates these silicon photonics? And there's a whole lot of fabs around the world with different capabilities. And these are just the industrial or the semi-industrial ones. There's a lot of university clean rooms that can also go to really high performance, just like the technologies that were just discussed in the previous presentation. So, but if you have these fabs, if you really want to scale to an industrial scale, can you actually build a fab? Can you use a fab or can you build a fab? And if you look at the costs that involved to make your silicon photonics, if you have to build a new fab, you need $1 billion at least. However, if you can start making use of fabs, making use of an existing process flow, making use of an existing fabrication run, at that point, your cost starts dropping dramatically. So if you can share costs, if you can standardize on a set of tools, if you can standardize on a process flow, or if you can share a fabrication run, these costs become accessible, even for small companies that have to launch a new product. But there's still a catch. If you want to design a new chip, it takes quite a lot of time, and eventually it still costs you quite a bit of money. So that means that making new chips is still a very costly proposition for silicon photonics if you don't have your own fab. So as a researcher, you either need your own facilities or you need a good design. And a good design is really important because in silicon photonics, because of that really high index contrast, every cubic nanometer matters. So you need that really good fabrication technology, but you also need that, that design to be able to cope with your problems of variability. And so how you do that, you can cope with variability, you can cope with the problems of imperfect fabrication in 3 different ways. One of that is investing very heavily in fabrication infrastructure. But in the end, that's only what the very top-end fabs can do. They can go to the really best fabrication technology available. But there's only a few that can do that in the whole world. So the second step is look at it at the design level. I mean, we know the variations in the fabrication. Can we design our devices or circuits that they are tolerant? So we need to predict upfront what the effect of variability is going to be. And the third one is to tune everything. If you basically make everything on your chip tunable, you add knobs which you can turn, which you can tune, which you can program, you can compensate for a lot of the problems that you find in photonic integrated circuits. So like I said, improved fabrication is probably the best way to do it, but it's the most expensive way. So you need to go to the best fabs in the world to do this. And this is out of reach of roughly any university in the world. This really is only available to the high-end fabs. So on the design level, there's a lot more possibilities, and coming up with smart design rules, smart methods to predict how a circuit will behave under variability is a really important research area at the moment. And it's under that there's a lot of space there to work, and there's really not enough effort going on to make this really worthwhile. And this is important because if you can't design a chip that is going to work upfront, where you cannot predict upfront that it's going to work, your basic entire design flow is essentially flawed, and you're basically just gambling. Now, the third way of coming up with designs that actually work is tuning, is essentially actively modifying your design on the fly in real time to compensate for its deficiencies. And that is a trend that we see more and more often. And it's also highlighted by Professor Das earlier that you need not just photonics, you need photonics and electronics. So you come to a system where you can control, where you can program everything. So we're moving slowly from a situation where you have very simple application-specific circuits to circuits where certain elements are tunable and configurable, like for instance, this double ring resonator filter, to circuits where you have multiple functions on the same chip. So you can do detection, transmission, to circuits that really have a programmable block where you can fully reconfigure a certain part of the circuit. For instance, by coupling to different inputs or switching the inputs to the outputs, to what I would call a general purpose programmable photonic circuits, like the type of circuits that are the subject of this excellence center that's also being pursued by myself and by Professor Kapmani at the University of Valencia. Circuits that essentially can be configured in software to do new things that can take input and output signals both in the optical domain and in high-speed electronic domain. So microwave and photonics. And at the center of this is something that is electrically tunable. So you have an entire mesh of waveguides where all the couplings between the different waveguides and the different paths can be electrically configured. Now, this would be a game changer. This would essentially allow anyone with a computer to start innovating, to start to do research and try out new things with photonics. If this works, you basically create the photonic equivalent of a Raspberry Pi, of an Arduino, of an FPGA, something that puts photonics in the hands of a community that is 1,000 times larger than the community that is doing photonics today. And it's incredible, in my opinion, what we will see in the coming decades that will come out of that community once these chips start becoming available. Now, we are not yet there. These chips don't work yet. So it's an ongoing research, and there's a lot of drive nowadays to build such general purpose programmable chips. So this is my intermediate conclusion. Photonic circuits are really a hot thing. I mean, they're the only way that you can scale up the manipulation of light to really complex functions. And they're empowered by the rapidly maturing chip technology, not just in university clean rooms, but also by industrial fabs that really make this technology ubiquitous available. However, because the circuits are becoming more complex, you need better design tools, and you also need to be able to predict how these circuits will behave. And one of these things that makes that prediction easier is the use of programmable photonics, is making photonics programmable. Now, if you have this whole field of photonics, where should you go? Where is the room to innovate? And here, I'd like to basically throw open a whole dish, a whole menu of possibilities where you can innovate. And this is a message to all of you, not just in this center, but basically in the whole research community. Where can you innovate if you want to do photonics? And there's a whole range of layers, starting from new materials. There's a lot of drive to integrate materials like graphene, or 2D materials like TMDCs, or new polymers, quantum dots. And that's just the bottom layer, how to bring these materials into the photonics. Then comes the question of how to fabricate these. Can we come up with better lithography methods like self-aligned structures or self-assembled structures? New ways of epitaxy or strain engineering. And once you have these fabrication methods, or you have a unique fabrication methods, you can put it to use to make new types of devices, building blocks for circuits, like photonic crystal effects, like photodetectors, like quantum devices, such as single photon sources or phase shifters. And a building block is just a building block. Like I mentioned, if you want to do something really complex, you go to a circuit. So can we build new functions, like putting some building blocks together that can do new things? Topological photonics was not predicted until suddenly someone came up with it. Quantum logic gates are really a big thing nowadays. And you can put them together into larger circuits to do wavelength filtering, dispersion engineering, real quantum processing. And you have passive circuits where you just use the flow of light, and basically all the information is processed in the optical domain. But it becomes really interesting once you start adding electrical functionality as well, like modulators, light sources, detectors, which allows you to do a whole new range of circuits that you can use. If you bring in the electronics as well, then you can make transceivers, then you can make an accelerator for AI applications, or kind of electro-optic oscillators. And finally, if you have these programmable photonic circuits, suddenly you can you can also not just innovate in the hardware, you can innovate in software. You can come up with new programs for these photonic FPGAs. And that's a whole new field. No one has really been playing with that. What can you do in terms of smart programs on a photonic chip? And so finally, you need to bring it to do something useful. So there's a whole range of applications that are lying wide open. Everything that you can do with light, you can essentially do with light on a chip. So there's a whole range of photonic application innovations available for you. So with that, I would say this is a kind of mission. Go forth and multiply the photons. It's up to you. There's lots of room for innovation. Thank you.
Yeah. Thank you very much, Professor Pimbogar. So now I think Professor Shayon, can you just take over? Maybe some questions and answers, I think.
Great. Yes. Can you hear me?
Yes.
Great. Thank you, Professor Bogarts, for a very exciting and interesting talk, as usual. You have a lot of questions, so I'm going to just go through some of them, and maybe the other panelists can also jump in. I'll take the first one first. What is the equivalent of a transistor in silicon photonics? Or to generalize it, should there be a transistor in silicon photonics?
That's an interesting question. Well, first of all, the functional equivalent of a transistor, I don't think you really need that in photonics. I mean, electronics is really good at doing that particular function. But if you look at the role of a transistor, like the transistor as the one building block that is used for everything in electronics, there's no such thing in photonics. You will need a combination of building blocks like modulators, detectors, waveguides, filters, together to build a circuit. So in that way, I think you could compare that to the combination of transistors plus resistors plus diodes plus capacitors in electronics. But there's no like one magic building block that does almost everything in photonics. You need that combination. So And for the actual function, transistors are good at one thing. They're a very highly nonlinear switch, which is something that photons are really bad at. So I think if you want to get the function of a transistor, use a transistor. I mean, it's very difficult to make the exact photonic equivalent of a transistor.
Awesome, that's great. Bijoy, do you want to add anything to that?
No, it's okay. I think that's enough said.
Let's move on.
Yeah.
So I see a flagged question here from Kumar Piyush, who I believe is one of your students.
Yeah.
What are the basic blocks in the active electronics control of large-scale programmable photonic circuits? And again, I think this is a question for
Okay.
Wim.
That's an interesting question, because there's still a lot of, I mean, people have been a bit of neglecting that area. And so at this point, I think most electronics control of a photonic circuit is a DAC, a digital to analog converter, which drives a current source or a voltage source, and an ADC, which reads out some monitor photodetectors. These are actually quite inefficient devices, especially if you need to scale them up to like thousands to drive a very complex photonic integrated circuit. So there's a bit of work around using digital driving, like pulse width modulation or pulse code modulation. But at this point, that's still very rudimentary. So today, the most common building block in a photonic control system is the DAC, the digital to analog converter. I think there's a whole lot of space in then adding feedback loops or control loops that read out a monitor detector and automatically adjust the operating point of the DAC, or doing that even fully in an analog system, because you can, for instance, make a PID controller entirely analog. And there's a bit of work, mostly I think from the Politecnico di Milano, from the group of Andrea Meloni, who have been trying to build these analog control circuits to stabilize photonic circuits without a need for an external digital to analog converter. But it's, at this point, most control systems are very traditional. So you have an FPGA or a microcontroller, you have a large number of DACs, and then you drive your photonic circuit. And there's a software layer that controls it all. That's very, very basic, but not very efficient. So a lot of room for innovation here.
That's right. Absolutely.
Yeah. Yes.
One of our panelists has his hand raised. Is that?
Yes, thank you. This is Janaki Raman here. Yeah, so thanks for that talk. That's very nice. And I mean, I'm from the electronics background, the microelectronics background, and you can assume that I don't know any photonics. So it's a very naive question that I'm asking. And I'm coming from the background of, VLSI and digital circuit design, right? So you said that what you have to do is to tune circuits, right? To account for variability and all that. So in digital or analog circuits, there is the concept of a multiplexer, right? Where I can actually multiplex multiple outputs to a single pad, right? And thereby I can actually tune, even internal parts of my circuit. Now, is that possible to do here in a photonic circuit? I mean, what is the equivalent of a multiplexer here?
Okay, I'm not entirely. Like you said, I'm not an I don't have a strong electrical background. So there we are, okay. Compatible. So I'm not really following what you mean with a multiplexer. But
okay. So what I'm saying is, you showed, one of these, complex waveguides and stuff like that, right? And you feed light through one end and the light comes out through the other end. Now, my question is, how do you tune an in-between block, right? Because the problem is, I cannot feed light into that block directly and look at the light out of that block, right? So, it goes through a lot of combinations.
So most of the tuning, most of the control of a photonic circuit is actually done electrically. So the light is the information, it flows, but the flow of information is controlled electrically. And that is done by a microcontroller or an FPGA and a set of DACs. If you want to know where the light is going, you need to put some monitors in between that are also read out electrically, and that basically the whole control loop that switches everything around in the flow of light is done in the domain of electronics or software. So
Okay.
does that answer
Okay.
your question?
Yeah. No, I think it's, I think I sort of get a feel for it, but maybe I'll discuss this with Professor Bijoy, and maybe I can write to you later.
Yes, I think.
Okay. Yeah. Thank you.
Vijay, do we have time for one or two more questions?
Yes, I think.
Okay.
I think particularly you can. I think that answer could be for you. That Umesh Chandra Siorpalli, what he wrote, I think you may be able to answer this thing. In the
Let me
context
skip
of,
that for a moment because that confused me as well.
I see.
So
Okay.
here's a question for Wim, which I think is a good one. What is the current progress in layering heterostructures on silicon photonic chips? I would imagine that it is difficult to adopt in the CMOS process. And I think this is something that many of us continually deal with. So many materials and so many constraints.
So the holy grail of integration is, of course, either depositing or epitaxially growing whatever material you need onto the silicon. And there are less restrictions on the CMOS fab than you would actually think. Well, at the large CMOS fab, what they mostly care about is contamination, so that the presence of a different material in the fab would not destroy their electronics processes. But it turns out that actually most materials that you need are already in some form or another used in a CMOS fab, with the major exception of gold. So there is quite a bit of research going on in doing, for instance, epitaxy of 3,5 materials of barium titanate onto silicon photonics in a way that is compatible with CMOS fabrication techniques. The alternative integration of whatever other materials onto your silicon photonics is basically just putting them down on where you need them, like physically taking it from another substrate and putting it down. So that's bonding techniques, that's transfer printing techniques, which is essentially pick and place, or the very coarse way to do it, flip chipping. So a lot of short-term research work and development is focused on this technique. For instance, the way that Intel integrates their 3.5 lasers on silicon is with a bonding technique. So I think in the next 10 years, most of the applications of weird materials on silicon, if you would call it that way, will be with some form of transfer printing or bonding technology. But in the long term, I think that, for instance, lasers integrated in silicon photonics will be epitaxially grown.
Great. On a sort of related note, could you comment on the new materials, especially for photonic switches? There's, I think, one thing listed here as BTO, which I think is barium titanium oxide or something. But yes,
BTO is barium titanate. Yes, so that's actually one of the big problems in photonics at the moment, is that there's no magic solution. What the holy grail of large photonic circuits is a tunable phase shifter, which you can then turn into a switch, essentially. A tunable phase shifter that has no loss, a very short length, a low driving voltage, and basically like it has a perfect linear operation. Now, there's quite some materials that do that in some form or another, and BTO is, for instance, one. But it's very difficult to integrate them in a way that you actually get the phase shifter that you want. Likewise, people are looking at 2D materials like graphene for this function, polymers even for the same function. But it's the difficult thing is indeed bringing it together with the silicon platform, not just from a compatibility of materials, but also making sure that by putting the materials together, you're not actually destroying their behavior, or you're not creating a lot of losses or backscattering. So today, I think that is, if you really want to scale up photonic circuits to like 100,000s of components and make them really programmable, that's the holy grail to strive for, is like that low loss phase shifter. It's much more important than the light source. It's much more important than the detector. It's really the one thing that will make a circuit programmable and scalable.
And I think we can also add to that, that as these very low voltage or low control signal techniques come up, they also become more sensitive to noise. So you could make a single photon switch, but it also is also very hard to use currently. So you said the advantage, how do you overcome, this is sort of scrolling in real time, how do you overcome the challenge of high power consumption due to the large number of active tuners in a programmable photonic circuit? Or is this a problem so far? Maybe PWM?
Well, it is a problem at the moment because the most common way of tuners, the most common phase shifter is a heater. However, if you find a technique that like a material like BTO, for instance, or like electro-optic polymers, if you use techniques like Pockels effect, then you're essentially electrostatically tuning. And at that point, the only power consumption is because you charge and discharge a capacitor in a non-adiabatic way. And that means that your power consumption on your chip will basically drop almost to zero.
So, so I wanted to add here, I think maybe you can comment, Beam or Ion probably. What about this phase change material nowadays people are talking for switching purpose? I think a lot of papers are also coming out lately. What is the prospect of that?
Actually quite, I have quite high hopes. At this moment, the problem with most phase change materials is that at least in one of the states, they're quite lossy. So you don't really get a lossless phase shifter out of it. It's more like an on and off switch. The second problem is that they're on one hand, they're zero energy because once they are in a state, they stay in a state, but the way to switch them is still with heat. So depending on how fast you need to switch them on and off, or how often you need to switch them on and off, they are either a very good or a very bad solution in terms of power consumption. If you constantly have to switch them on and off, they're essentially not better than a heater. But if you basically can leave them for the same state for hours or days, they consume zero power and they're very good.
Yeah.
There's also the MEMS technology that is also improving, and they have very high extinction ratio and they don't age as much as some of these materials. So we don't know yet, I think, which is going to.
Exactly, yes. We're also doing quite a lot of work on that in that direction with silicon photonic MEMS. And the nice thing is that MEMS don't need any new materials. They essentially can be processed directly in the fabs that are currently doing the silicon photonics. So that's an interesting proposition. They are already compatible in terms of materials.
All right, let's see. Still many questions to go. Here's an interesting one, actually, because he asks about so I'm going to paraphrase this. How is silicon photonics relevant to biomedical equipment or biomedical applications? In particular, do you see a big application area for photonic sensors, built using microchips or programmable microchips?
Yes. Well, there's I think by now the quite well-known example of like using silicon micro ring resonators as a biosensor. That's a very useful, potentially really high volume application of silicon photonics that could revolutionize healthcare. But then you can use the optical functions of silicon photonics as well. I mean, for instance, there's been quite a bit of work on optical coherence tomography, where you use silicon photonics chips, or where you basically use light to image your skin or your teeth or the back of your eye, your retina. If you can use a photonic chip to integrate that functionality on a chip, you suddenly have a much more cost-effective solution to solve medical problems for a lot of people. So there's continuous monitoring. One example that I like to talk about is, for instance, continuous glucose monitoring for people with diabetes. There's a spin-off from our university who is building a silicon photonics spectrometer on a chip that can be implanted in your body and continuously monitors your blood for the sugar or the glucose values of your blood. So you have a continuous monitoring of your level of glucose. So I think that there's plenty of applications. I think we'll see an explosion of applications, especially when we can put photonic chips in the hands of a lot more people that probably don't know a lot about photonics, but they have good ideas. And that is also one of the reasons that I think programmable photonic chips are so important, because they can put these photonic chips into a community of smart people that don't know how to design a chip, but they know a problem and they have an idea of how to get to a solution. And I think that at that point, we'll see an explosion in new biomedical devices that we haven't thought about today because the technology is just not there.
It's awesome. Let's take at least one more, which is that we have talked about silicon, but there's one question here about indium phosphide, which I'm going to sort of turn around and ask. What do you think, Wim, is the future of indium phosphide photonics? Is it yesterday's integrated platform, or is it here to stay?
No. Well, I won't give an opinion in the long term. Like, I have no idea where 30 years from now, how the silicon and indium phosphide will play out. I think at this point, for medium-sized photonic circuits, indium phosphide is probably the most powerful technology around. It has basically almost all the essential building blocks. The only thing that goes, or the only two things that go against indium phosphide at the moment, is that its passive waveguides are a bit more lossy than you would find in other platforms. And because the index contrast is modest, not very high, the integration density does not at this point scale to the same level as silicon photonics. So you don't go to 100,000 components on a chip, but you can still go to thousands of components on a chip. There's research going on to basically work on those two weaknesses. So it might well turn out that for the coming couple of decades, indium phosphide is still a viable technology. But unless they find a way to really scale it up to the same volumes as silicon photonics potentially can go, using 200 and 300 millimeter wafers, there might still be a limit to how widespread indium phosphide could be. I mean, you can compare it to electronics. There are still 3-5 electronics for specialty applications. And in some fields, these are still the best electronics around. The best transistors, the fastest hemmed transistors, for instance. Just like you have silicon germanium by CMOS as specialty electronics as well. But the dominant electronics is CMOS. And my guess is that we're going to a landscape where the dominant photonics is going to be silicon photonics in different flavors. But you'll still find a market for all these technologies that can do certain things better than silicon photonics will ever be able to do. Would you include organic photonics in that umbrella? Yes, because the potential for organic photonics, I think one typical thing that stands out is that it can possibly be made extremely cheap, an order of magnitude cheaper than a silicon photonics chip, and it can be biodegradable. So for disposable devices or devices that need to be like safe, for instance, in the food industry or something like that, it might turn out that organic photonics or polymer photonics is by far the best solution, especially if you don't need super narrow waveguides. I mean, if you can live with a large circuit, if you don't need to put it in an ultra small device, polymer photonics might be the cheapest solution and good enough for what you want to do. All right. Okay. Bijoy, how about, do you see some questions that you want to pick out? I think we've covered a wide range of topics here.
Yeah, I think
so that's really
we cannot answer all the questions, but I think we will maybe we'll try to answer maybe offline some of the questions, because we have
be very helpful.
Yeah, so we'll be just taking all the questions, and we'll be trying to get answers from all the panelists if possible, and we'll forward to you, because we have taken enough time, I think, exceeding.
I'd like to add one comment on the first question that was asked about the transistors. And I said that, okay, it's not a good idea to do a photonic transistor.
Yes.
Now, I'd like to take that back, because I ended my slides with challenging you to come up with new ideas and come up with new ways of doing things and innovations in photonics. And then the worst thing that I could have said is, don't do this. So if any of you can come up with a viable photonic transistor that operates, let's say, at 300 gigahertz, wow, please do it.
I agree. I mean, there have been papers sort of describing what a transistor should be, but even going beyond that, I would encourage the audience to think of, what else a transistor can be. Transistors have been used in microwaves for things beyond digital logic. And you can still use them as mixers. You can still use them for neuromorphic, like analog schemes. And you can just use them for feedback. And as we know in optics, feedback is horrible, but also very useful if you want to narrow the line with a laser or even do some computations. So I completely agree with Wim that we should think of the words that we are used to, such as transistor, diode, resistor, and sort of ask if they are exactly the same.
In that case, one could go for digital photonics, like digital electronics. You could think of digital photonic circuit also.
I always say that, when I started the field, it was called quantum electronics, and it was neither quantum nor electronics.
Most of the devices are classical, yeah.
Yes.
Yeah.
But now we are getting to the phase where photonics involves quantum and involves electronics. So great, this was fantastic.
Exactly. Yes.
Thank you, Thank you, Vijay. This was a great question and answer. I hope we can answer the rest of the questions.
Yes,
offline.
of course. Yeah, offline. Yeah. Thank you very much. Thank you, Professor Beam, for your time and a nice talk and all the answers. Of course, our audience got some benefited, of course, and Sion for your nice presentation as a moderator and also your interaction and also constant touch with our group. Thank you very much. And over to Global Engagement Office, please.
On behalf of Office of Global Engagement at Madras, I would like to thank all the panelists and the moderator for today. So I hope the audience found the session useful. So yeah, with this, we end the session. Thank you.